slope fields and numerical methods. So sometimes you get a differential equation that you don't know how to solve algebraically. So that's really what we're looking at today. Okay, so what do you want to think about what a differential equation means? So if you look at this example here, dy dx, so this is in terms of x and y, but we can't represent it as a function of y over x. We can't, it's not a linear where we can find an integrating factor. We can't separate them. But this represents the slope, okay, at any particular x and y value. So these graphs here, you can see, have little lines. Okay, those little lines represent the slope of a tangent at that particular point. So if you put in an x value and a y value, you find that point on your graph, and then these lines represent the slope. So basically, if you've graphed all of these, you can tell your graph is going to be going this way, an increasing function, right, with a curve to it. Same thing here, okay? These two graphs we can use for this particular function. Notice just the scale, right? So that's the only difference here, is the scale on them. So it says state the window for each slope field. So this one is going from -1 to +1, and the markings here would be 0.1s, and then same, it's squared, so same for the y's. Whereas this one is going from -5, that's -2.5, right? I'm going to look online, yeah. So it's going from -5 to +5, and that marking would be 0.5s. Okay, so this would actually, be, you would have more accurate, closer. Obviously, you're only going in that domain, the x between 0 and 1, and y between 0 and 1, okay, or -1. So notice how there are no slope fields here. Why is that? Because it doesn't make sense. So if you took a value, an x value that's negative and a y value that's negative, that's in the third quadrant, you'd be taking a root of a negative, which you can't do. So it's only defined for when x plus y is greater than 0. That's why you can't even draw slopes there, based on this particular question that we're doing. So the slope fields are for a particular differential equation. You don't just draw a random slope field. You have to, and most likely you'll be using a computer to do this for you. Okay, so I'm going to go to the next. Actually, just going to double screen this. Okay, so examine both carefully and notice where the line segments are drawn. Okay, explain why the gradient line segments do not cover the entire grid, because you can't take which leads into this, x plus y has to be greater than or equal to 0. Okay. So then it says sketch possible solution curves passing through points 0.5, 0.5 on the first graph. Okay, so we know 0.5, 0.5 is about here, right? So your slope is going to be exactly that line segment. Okay. And then you're going to estimate based on, so for example, if you chose these two values, you're going to want to follow these slopes as best you can. So in this case, oops, that's not great. Give me a second. Here, passes through that point, so that slope. So I can graph, it looks something like that. On that graph with those slopes, I can't get it to go quite through 0, 0, right? But what should happen at 0, 0 in terms of the slope? You put 0, 0 in there, the slope is 0. So it should be a minimum, right, or approaching that, okay? Which it pretty much is there, so it's a little hard to get too accurate. In this one, 2, 3, so 2, 3 is sort of here, so it's going to be kind of like that. And then here, so it's going. So if you have to do this on a test, you're just trying your best. Use pencil, right? And I'm not going to be looking, it's not going to be exactly the same as on yours. Yes, Ron?
When you're not supposed to draw lines and estimate the value.
Because you're estimating what the function is. I don't know do you know how to integrate and solve that differential equation y over dx? Root of x plus y? No. So this is just another method. So in this case, we're actually going to draw the slope field for ourselves. This one we can do. Yep. These ones here or this one? This, you try to follow the shape of each of the slopes as you, so every point here, that should have the same slope as any line approaching it. Then this one should be the same parallel to that. This should be parallel. And you just keep following it down. Like you're not going to go against the slope, right? So you're not going to change. So if it should tell you one point that it passes through. So that you use the actual, so I use the actual slope line that was there. And then from there you have to follow the slopes. Lesson. Okay, so this one, we do know how to solve that differential equation, but we're going to use it using slope fields, and then we can kind of compare, right? So it says sketch a slope field for that function on the grid, then draw a solution curve. So 1 over 2y, this is your slope. So we want to find, basically, for each of the y values, we want to draw those little lines. Okay, so when y is 1, for example, your slope is a half. So for any x value, when y is 1, your slope is a half. So slope of, let's look at this. If the slope was a half here, this would be up 1 to the right 2. So it's going to, like if you were to show the whole thing, it would be like that. Or extended, but obviously a slope field, we're just showing it in parts. Okay, so that's your line, and you're going to do the same all the way across. So those are all parallel. Actually, what would be easier if I did is actually the line function. So give me a sec here. You can start doing that. Get out a straight edge. That would help. So I'm actually going to erase these and use my line. Okay, so up 1 to the right 2. So basically, okay, so then I'm going to make this smaller. Okay. Cool. then for when y is 2, that's going to be 1/4. So when I do 1/4, so that would be, say for example here, up, so up 1 to the right 4, so I'd be going from here to there. Oh no, that's up. Alright, so like this, and then okay, first easier than this. Okay, so then, oh no. Okay, pretty close. So there. Okay, underneath it'll be negative slopes. Oh, we got a phone call. Oh. All right, so then these ones are going to be, these ones underneath will be reflections because they'll be negative. Obviously, when y is 0, this is undefined. So that tells you that your graph is going to have a change in direction, okay? So looks like here it's going this way, and then it's going to come back because these are all reflections of each other. So this is going to have, so this will be negative 1/2, so down 1 to the right 2. You can work ahead if you've done this. I'll get this done here. And then what we want to do, this would be negative 1/4. So from here, then I want to write 4. And then not. Okay, so that's kind of enough right now because it says draw a solution curve through the point 1, 2. So if you, I'll do, so 1, 2 is there. Okay, so it's gonna have that slope of that line that's passing through there. And then you can see it's going to curve around. Now in this case, so if we follow this with that slope, it's got to be the same here, which is steeper, and then that. Now if you actually solve this equation, you'll see that mine is not entirely accurate. Okay? Where should this point there be? Exactly. Sorry? Coordinates of that point there where it changes direction. -3, right? So I'm a little bit off with this. Okay? So we've drawn a possible solution curve, algebraically determine the solution. Because we can actually do this algebraically, we can test it, right? So this is 2 dy. Actually, I can take the reciprocal. So this would be x dy. Now it goes through the point 1, 2. So c equals -3. So x equals y squared minus 3. So x plus 3 equals y squared. Y equals plus or minus x plus 3. Okay, and so you can see there that the vertex of that radical is at -3. Is that a handout?
Yeah. Can it be only the positive because the condition that you're given is just a positive side of it? Or is that not the case? You're given 1, 2, and not 1, -2, right?
Well, that's just one point though. So 1, oh, I see. Well, no, it would go through all of this based on that function.
Okay.
But 1 point, when x is 1, we do get 2, right?
Mm-hmm.
We also get -2, so that's just another point on the function.
Okay.
Yeah.
Well, would you expect it to draw slope on
No, we would probably give it to you.
Okay.
Yeah. Okay. Takes too long. I'm really not wanting to test you on if we could do slope things, right? So sketch possible solution curves passing through the points 0.5. Yeah, that is like, did I delete that from yours?
Yeah.
Yeah, okay. That's the last question. We just copied it onto this incorrectly. Okay, so that is slope field. Now, another method, I think some of you have actually investigated this on your own, is, and I say it Euler's method, but I think Euler is maybe how you're supposed to say it. I don't know. Whoever taught me way back when said Euler to me, so E-U-L-E-R, that mathematician's method. We use that a lot. Okay, so how can we find the graph of the solution curve to known differential equations if we can't do the antiderivative and we don't want to do a slope field? Because we've just seen that it's time consuming. How do we find the points on a solution curve without knowing the equation? So what can we do? So this particular example, again, this is the first one that we had. It says, what if we know the differential equation? We're looking at this particular one. We know that it passes through a certain point. Obviously, we can find the rate of change at that point. Okay? So we know the rate of change in y with respect to x, and so therefore we should be able to find a new y value if x changes by a certain amount. So we're kind of estimating. This is an estimation, again, kind of like a slope field. So we're going to say, okay, if we increase x by a certain amount every time, what happens to y? Based on the fact that we do know the slope. So the slope is going to be proportional to that, basically. So here, at the point 0.2, we know the slope, okay? It's the root of 0 plus 0.2, okay? And so find the decimal form of that. So you'll need your calculator. And it does say 5 decimal places, so 4, 4, 7, 2, 1. Okay. Now, we need to think about what happens. So, slope of the tangent. Remember back to math 10. It's the change in x over the change in y over the change of x, and that's equal to dy dx. Okay, so our change in y is, so here we have some function, some curve, right? You have your slope of your tangent at that point. We basically now want to use the slope to get an approximation for another point. Here it's quite far away, but maybe it'll be closer. So really, your change in y, which is this column, if we solve this, is your change in x times the slope. Okay, we're just rearranging it. So change in x, you have to decide what's your change in x going to be, right? So in this case, we're telling you, we're going to go by 0.2. All right, you can make it smaller. We'll look at what happens if you make it smaller, if you make it bigger. So we're going to do 0.2, and then we need to multiply it by that slope, okay? So we're really trying to find this. So this is delta x, this is delta y. We're trying to find what that delta y is based on the slope back here and your change in x. So just multiply here. This is your formula. So 0.2 times that value. It's in your, there it is. So I'm going to copy that out. That times 0.2. Okay, and then 5 decimal places. Yeah, but just keep it in your calculator. So now our new y value is the previous y value, because this here, this point, was x, y. So now our new y value is whatever y was there, plus delta y. Okay? So we need to add plus the change in y with 0.2. So that's going to be 0.28944. So now you have your new x and y. So now our x is 0.2, and our y so now you add 0.2, and then square root that. And then multiply that, dy dx, by your change in x, which is 0.2. And then you add on here your previous y value. If you still have it in there, actually, you could do that. can punch later. Okay? Alright, so we just keep working through this. So that's going to be now 0.4. So that answer plus 0.4. And then square root it. 0.91069. And then multiply that by 0.2. And then add the previous y value. And then from there, add 0.6. There's that. 0.2. The previous y value. And 0.8 to that. Let's go read it. Okay, that's 0.2. Add the previous y value. Okay, so we now have 5 points, right, here on our, well, actually we have 6, right? So these are your points in terms of writing them out. You can go to all the decimal places, but you're not going to be able to round to 5 decimal places on the graph that we give you. So if you want to round to say 3 decimal places, you can. So 0, 0.2, 0, 0.289, 0.2. I'm going to add in the last one, 1. Okay. And then sketch those. I'm actually going to keep it maximized. Okay, so on the graph, the actual graph is done for you. We are going to sketch these. So 0, 0.2 is done. 0.2, 0.289, You can see it's off already. 0.4, 0.42, so that'd be 529 would be about there. 0.6, 0.611 be here. So we'd be joining these like that, and it's off, right? Based on, because we're estimating. Okay, so obviously, the error can be minimized if we make this shorter. Okay, so if we find more points, make our change in x smaller, then we're going to get more line segments that will likely be better, closer when we're doing it like that. So error can be minimized by reducing the length of the tangent segments, which is accomplished by reducing the change in x. Okay, if the change in x is reduced by half, the amount of error is also reduced by approximately a half. So then we're just going to look at a table of values of calculations that have been done. Okay, I think they show some like this in your textbook as well. So there's your x values. Here, these are the exact. So this is your exact values. So that's the graph that was already given. This one, these are our approximate with changes. So these are your changes in x. So we went up by 0.2. Okay, so you can see here that these are all the values that we got in our chart. Okay, so when we went by 0.2s, we got 0.289, 0.429. So those compare to our chart. Okay, if we make the change in x 0.1s, then these would be the values. Okay, so if you compare these to what they actually are, this is getting a little closer. 0.05s, they're getting really close. Okay, so the smaller that change in x, obviously, the more accurate you get. These are the actual errors that are calculated, so the difference between these. So you can see the errors are getting smaller. Okay, obviously closer to that original point is better, but they are getting smaller. Okay, so what happens to the error values for 0.2 as the size of h is reduced by half each time? So we're looking at the error values. So going from here, so that you can see is about half as much as we estimated. Okay. I'll call it original errors. Okay, what you will notice though, as the number of steps increases, then the error does increase as well, because you're getting further away from that exact point that you do know. So as you're going further away, because each time there's a little bit of error, so they build on itself. Just like when we graphed on ours, that wasn't too far off, but it was further off here. So as your number of points increases, your error does increase. So number of steps is the error. So just be aware of that. Okay, and then let's just get, I want to get my data here. Okay, so let's just look at your data booklet. And okay, so in the calculus, topic 9 calculus section, it'll be in a different section in the new data booklet for this year. But there's the formula for Euler's method, basically what we just did in that chart. Okay, so what does H represent here? That is the delta X that we did, the change in X. Okay. And then it says, what does F, X, and Y, N represent as it relates to Euler's method? So that is your dy dx that you evaluated at points X and Y, whatever point that was your derivative. Okay. So we took your y value and added dx times the derivative at that point. That's how we got the next one. Okay. And then obviously your x's are wherever you're starting with, and you add that change in x. You're just adding the h or change in x each time. So that actually is given to you in your data booklet. If I'm asking you to do something like this on a test, I will give you the charts. So it's kind of a little more obvious in that sense. Chart just like the last one, or the last one here. Solve this, taking steps of h equals 0.25. So this one you do have to set up your chart, but if I put it on test, I'm going to have the chart for you. So you want to do the same thing here as we just did. There's not a whole lot of space, so you might want to get a separate piece of paper, but you're going to just make up your chart. So if we're starting at 0, 0.25, 0.5, 0.751, and then we need our x, we need our y, we need our dy, we need our I guess probably one more. Oh, it's not. So we need your x, your y, your x, and then your yeah. So we're starting at, so when x is 0, 0.25, 0.5, 0.75, 1. Okay, so if x is 0, we can start with a y value. So if x is 0, let's start with a value that we do know how to do cosine. Let's make y equals 0. Okay, so the y value wasn't given to you, but let's start with coming up. You choose what y value. 0, 0 would be the easiest. Okay, so then cos of 0 is 1. Okay. So then dy is, remember, dx times your, your
dx, which is 0.25, times your derivative, so that's going to be 0.25. Then you add that onto your y. And then you're taking, okay, so quarter plus a quarter is a half. Okay, close of
Half of the half. Get your calculator out. You'll need your calculator in radian mode.
No radian. Okay, so then we're going cos of 0.5 times half is half is half.
Take that, multiply by changing x.
Two, 4, 2, 2, 3. Okay, add on previous y. Okay. Take that y, add on the x, times by half, then take the cos, answer. Add on the 0.49. Oh, no. So then this will be what you can use to estimate your curve. So if you wanted to solve that and graph it, you're going up by 0.25, so it'd be good if you had a ruler to estimate. I'm just estimating here, and up by 1 the other way. Okay, so 0, 0, 0.25, 0.25, a little higher, 0.5, a little less than 0.5, 0.75, a little less than, so 0.71, and 1 is 0.89, I like that. So it's kind of going to be curvy.